Identifying digital information is only half the value that hashes have to digital forensics. In addition, hashes can also tell you when digital information has been changed. Before I tell you about that, you need to understand just how hashing works. Let's look at that now. So how does hashing work? Well, we don't need to get into the mathematics of it because we have hashing tools that do that work for us. So instead, let's look at some examples of how hash values relate to the digital information they are derived from. Say that you have a computer file that contains the characters, "Quick brown fox jumps over the lazy dog." You run this file through a hashing tool and the following numerical output appears. This number is a hash value of the input string, "Quick brown fox jumps over the lazy dog." A hash value is a single number, an integer, that uniquely identifies the information contained in the file's digital fingerprint. The mathematics of hashing guarantees that the same information input will always produce the same hash value output. If we change the input, even slightly, by, say, appending a period to the input string and recalculate the hash value, the resulting hash value will change. Notice that the hash value of the changed string is not just a little bit different from the previous hash value, but is a lot different, even though the string was changed only by appending a single character. Now let's capitalize the first letter in the input string and recalculate the hash value. That's right, the hash value of this third string is different and very different from the hash values of the two previous strings. All we did was flip the value of a single bit in the input string, which is the smallest change you can make, and the resulting hash value is completely different. This is why cryptographic hashing is very useful for detecting if digital evidence has been changed, and also for verifying that digital evidence hasn't been changed. There is also another reason why the randomness of hash values is important, and I will cover that reason shortly, but for now, there may be another question on the tip of your brain. If you have never seen a number that contained alphabetic letters, welcome to hexadecimal notation. Hexadecimal, or just hex, is a base 16 numerical system that uses the numerals 0 through 9 and the letters A through F as digits. The letters can be written in upper or lower case, and never mix the case of the letters within the same hex number. Because a hexadecimal number does not always contain letters, you will often see additional notation indicating the number is hex. This keeps you from assuming the number is base 10 decimal, which is what we humans are all accustomed to seeing. Hash values are usually written in hexadecimal notation for no other reason than very large numbers can be represented using fewer digits when written in base 16 hexadecimal numbers than when written using base 10 decimal numbers. What you see here are the same integer values written in decimal and hexadecimal notation. Yeah, the difference in length between these numbers is only 8 digits, but when your forensic documentation contains hundreds or thousands of hash values, you will be glad you are using the more compact numbering system. And anyway, you're always going to see hash values written in hex, so you really need to get used to seeing letters as digits. Nobody will be asking you to recite hexadecimal numbers in court, so it's really not that bad. Now, there are a few more things you should know about hash values before using them. I mentioned previously that hash values are not reversible. That is, there is not enough information in the hash value to reveal the original information that was hashed, or to discover the type of information the hash represents. This irreversibility is why you will often hear cryptographic hashing described as one-way hash functions, to differentiate it from other types of non-cryptographic hashing that are reversible. Sometimes you will also hear hashing described as one-way encryption, which is incorrect. Encryption is specifically designed to always be reversible to allow recovery of the original input information. So the concept of one-way encryption makes no sense and would basically be a random number generator. The best way to discover the source information of a hash value is to literally guess what the original input is. This is called a brute force guessing attack, meaning that every possible input value is hashed until the same hash value is created. When using the brute force method, you may get lucky with your guessing after only a few quintillion tries. That many guesses, however, can take a few human lifetimes, so you better guess wisely and quickly. Hash values are always fixed in size. No matter how large the input, the hash value output will always be the same size for the specific hashing algorithm. Common sizes for hash values are 128 bits, 160 bits, and 256 bits. The size of a hash value is represented by its length in bits, which is an extremely large number. And the larger the hash value, the more reliable it is. Let's take a look at what I mean. The hash size of a hash value determines how many different numerical values can be represented by the hash value. The more bits there are in a hash value, the more unique items of digital information that can be represented by the hash value. You're probably familiar with the idea that an 8-bit integer can store 2 to the 8th power, or 256 different numerical values, specifically representing the values 0 through 255. A 128-bit integer can store 2 to the 128th power different values. In decimal numbers, that's 340 undecillion unique hash values, each representing a unique digital item of evidence. Yes, an undecillion is an actual number. Notice how much space the hexadecimal notation saves compared to the decimal notation. I'm just saying. Before you start pondering just how large 340 undecillion is, you might think, why would anyone need such large hash sizes? One word: collisions. Because there is a finite number of unique values that can be stored by a fixed size hash value and a virtually infinite number of input values of digital information, there's a mathematical possibility that two different input values will result in the same hash value. This is known as a hash collision, and the probability of their occurrence reduces the reliability of a hashing algorithm to unambiguously identify unique digital input. Here we see two different digital files, each with different content, that has resulted in the same hash value being produced by the same hashing algorithm. This is a hash collision. Collisions are both extremely rare and mathematically impossible to prevent, but the probability of their occurrence can be drastically reduced by increasing the length of the hash value that a hashing algorithm produces. Each bit added to the length of a binary number doubles its numerical range. By increasing the bit length of a hash value, we increase the maximum number of unique input values that the hash value can represent, and therefore gain a greater assurance that any calculated hash value will only represent one unique input. So how do we increase the hash value size? By choosing which hashing algorithm to use.